Hello and good morning to all of you. I hope all of you are doing well and all of you are in good health. If you remember, in the previous class, we had discussed some of the notable features of 8086 microprocessor, wherein we had discussed the operational capability of 8086 microprocessor. We had discussed the size of 8086 microprocessor ALU. We had discussed about the size of 8086 microprocessor, internal and external data bus. We had also discussed about different versions of 8086 microprocessor, where we had seen that there are three different versions of 8086 microprocessor, operational at 5, 8 and 10 megahertz. Then we discussed the various CPU hardware registers of 8086 microprocessor, where we had seen that there are 14 CPU hardware registers that can be categorized into 5 identifiable categories. And we also learned that each of these registers are of 16-bit in length. Namely, the categories were general purpose register, segment register, index and pointer register, instruction pointer, and flag register. We also learned that there are 4 general purpose register, 4 segment register, 4 index and pointer register, 1 instruction pointer, and 1 flag register. Then we discussed each of these registers and learned about their features in detail. Now, in today's class, moving forward, we will discuss three additional features of 8086 microprocessor. These are instruction queue, operational modes of 8086 microprocessor, and the programming model of 8086 microprocessor. To begin with, let us try to understand what is instruction queue and what is its utility. Before understanding instruction queue, it is very important for us to understand that 8086 microprocessor has two functional units. These functional units are the bus interface unit and the execution unit. The bus interface unit and the execution unit has its set of role well defined. The execution unit is responsible for decoding or execution of the instruction as specified by the name. Whereas the bus interface unit is responsible for making available the instruction byte and the data byte required by the execution unit in order to execute the instruction. It is also to be noted that while the execution unit is decoding or executing the instruction, it does not make use of the bus interface unit, which allows for use of the bus interface unit in order to prefetch a sequence of instruction byte that the execution unit is to execute at later instance of time. Now, this process of prefetching a sequence of instruction byte is called as instruction prefetch. So, when the execution unit is ready to execute the next instruction, it reads the instruction from the sequence of prefetched bytes and then it performs the required operation. Now, in order to facilitate the storage of the prefetched sequence of bytes, bus interface unit has in it an implementation called as instruction queue. 8086 microprocessor has an instruction queue of 6 byte in length. This implies 8086 microprocessor's bus interface unit can prefetch a sequence of 6 bytes and store it in instruction queue. Subsequently, the execution unit can take the instruction byte from the instruction queue and perform the necessary operation. The process of prefetching set of instruction bytes while the execution unit is performing execution of instruction is called as pipelining. Again, I'll repeat it. The process of prefetching set of instruction byte while the execution unit is executing instruction is called as pipelining. Now, this allows for enhanced performance of the microprocessor. Due to this overlapping of instruction fetch with instruction execution leads to increase in the processing speed of the microprocessor. But mind you, pipelining does not reduce the total amount of time required for executing an instruction. Again, I'll repeat it. Pipelining does not allow for reduction in the total amount of time required for executing an instruction. It allows for increase in the number of instructions executed per unit time, which is also referred to as instruction throughput. So pipelining allows for increase in instruction throughput but does not allow for reduction in time required for executing an instruction. But one of the major limitation of instruction queue in 8086 microprocessor is that, as I've already specified, the length of the instruction queue in case of 8086 microprocessor is only 6 bytes. So it can only prefetch 6 bytes of instruction and place it in the instruction queue. So this is instruction queue and its utility. Now let us move on to various operational modes of 8086 microprocessor. As learned before, 8086 microprocessor supports two modes of operation. These are minimum mode and maximum mode, or uniprocessor mode or multiprocessor mode. Minimum mode, as the name says, it refers to a situation where there is only one microprocessor in the system. So minimum mode is suitable for system having a single processor, which implies in such situation 8086 is the only microprocessor present in the system and all the control signals are given out by 8086 microprocessor. Categorically, 8086 operates in minimum mode when the MN/MX pin of the 8086 microprocessor is at logic 1. So this is to be remembered. We'll be discussing MN/MX bar when in detail when we will be going through the pin configuration of 8086 microprocessor. As understood, minimum mode has simple circuitry compared to that of maximum mode. So again, I'm repeating, minimum mode refers to a situation where there is only one microprocessor in the system. Likewise, maximum mode is suitable for system having multiple processors. Here, there exist more than one coprocessors in the system. So here, as understood, there are more processors connected to 8086. So we can have processors like 8087, 8089 connected to the system where 8086 is present. So when there exists more than one coprocessor in the system, there has to be needful coordination between the coprocessor for use of the global resources. So here it is to be understood that there can be two types of resources associated with microprocessor based system: global resources and local resources. Global resources are resources that are shared among cooperating coprocessors, whereas private resource are the resources that are private to or local to a given microprocessor. So when a set of microprocessors or coprocessors are sharing global resources, there has to be needful coordination with the in between the microprocessor of the global resources, because no two microprocessor or coprocessor can use the system buses or the global resources at the same point in time. So this is to be understood. Now maximum mode of 8086 basically allows for multi-programming or facilitates multiple programming. So this is the major distinction between minimum mode and maximum mode. So minimum mode refers to single processor mode, whereas maximum mode refers to multi-processor mode. In case of maximum mode, it is to be remembered that there has to be needful coordination between the various coprocessors for the use of global resources, because no two coprocessor can use the global resource, a particular global resource at the same point in time. Now let us move on to 8086 programming model. Now 8086 programming model basically tries to reflect the various internal registers that are accessible to the programmer in order to realize a programming construct. Again, I'll repeat it. 8086 programming model reflects or represents the various internal registers that are accessible to the programmer that the programmer can use in order to write a programming construct. Now, here there is a pictorial representation of the 8086 programming model, wherein we have four general purpose registers, namely AX, BX, CX, and DX. AX refers to accumulator, BX refers to base, CX refers to count, and DX refers to data. Now, all of these four general purpose registers are 16-bit in length and be further decomposed into 8-bit registers, or can be used as a collection of 8-bit registers. So AX has AHAL as its 8-bit representation, BX has BHBL as its 8-bit representation, CX has CHCL as its 8-bit representation, DX has DHDL as its 8-bit representation. So based on the requirement of the programming construct, we can make use of AX, BX, CX, and DX, or AHAL, BHBL, CHCL, DHDL. So these are the representations of the four general purpose registers that we have. Then onwards, we have two indexed registers, namely SI and DI, which stands for source index and destination index. We have two pointer registers, BP and SP, which stands for base pointer and stack pointer. We have one instruction pointer. Now all of these five registers, SI, DI, BP, SP, and IP, that is source index, destination index, base pointer, stack pointer, and instruction pointer, are of 16-bit in length. These five registers are used as offset with the segment registers in order to create displacement to access specific byte in the segment. So we'll discuss these five registers in greater detail, but for now just remember that these five registers are used as offset with respect to the segment registers in order to create a displacement to access specific byte in a given segment. Further, we have four segment registers: CSR, DSR, SSR, and ESR. These segment registers are also 16-bit in length, that is capable of representing each of this segment, or each of the segment register stores the base address of the segments that are present or assigned to a given program. So you can have, for a given program, you can have code segment, data segment, stack segment, and extra segment. So these four segment registers are capable of representing each of this segment or stores the base address of each of these segments. As we have understood in the previous class, that the overall memory of 8086 microprocessor is partitioned into logical groups known as segments of 64 kilobyte. So each of these segment register will be capable of pointing to the segment of 64 kilobyte in size. So we'll discuss each of these segment registers in detail in the upcoming slides. Then further we have a flag register, which is also of 16-bit in length, wherein 9 bits are active and 7 bits are left unused. Out of the 9 bits, we have learned that 6 bits are used in order to represent condition or status, whereas 3 bits are used in order to represent control flags. So altogether, there are 14 CPU hardware registers in case of 8086 microprocessor with their specific purpose, wherein we have 4 general purpose register, 2 index register, 2 pointer register, 4 segment registers, 1 instruction pointer, and 1 flag register. So this is a very simplified pictorial representation of the 8086 programming model. Now let us discuss each of these registers in detail. Now, as said, the programming model has 4 general purpose register, 4 segment register, 2 pointer register, 2 index register, 1 instruction pointer, and 1 flag register. Now, let us try to understand the purpose of the general purpose registers. So, AEX register, which is also known as accumulator register. Accumulator is used in order to perform arithmetic, logical, and data transfer instructions. Again, I'll repeat it. The accumulator register is used while performing arithmetic, logical, and data transfer instructions, or in the execution of arithmetic, logical, and data transfer instructions. It is also used in multiplication and division instruction in order to store the operand. So, in case if you are performing 16-bit operation, we'll use AX. And in case if you are performing 8-bit operation, we'll use AL. So AX stands for accumulator, and it's used while performing arithmetic, logical, and data transfer instruction, and it's also used while performing in multiplication and division instruction in order to store one of the operand. And in case if you're performing 16-bit operation, we use AX, and in case if you're performing 8-bit operation, we use AL. Likewise, BX register, it is also called as base register. BX register is used as an address register. It is used in order to point data in the memory. Here it is specified that it is used in base index or register index addressing mode. We'll come to this when we'll be discussing addressing mode of 8086 microprocessor. But for now, just remember that BX is used as an address register in order to point to data in the memory. Now CX register. CX register is also called as the count register. This register serves as a loop counter. So CX register is used as a default register while performing loop related instructions. CX register is also used in addition to loop instruction in performing string related operations and shift and rotate instruction. So in addition to performing loop related operations, it is also used in performing string manipulation and shift oblique rotate instructions. Now DX register, it's also called as data register. DX register is used in order to host the post number while performing or port number while performing IO operation. It is also used in order to hold the operand during multiplication and division instructions or execution of multiplication and division instruction. So this is the utility of the 4 general purpose register. So AX accumulator is used in order to perform arithmetic, logical, and data transfer instruction. It is also used while performing multiplication and division operation. BX, it is known as base register. It is used as address register in order to point to a specific location in the memory. CX, it's known as count register. It is used as a counter variable while performing looping operations. In addition to that, it is also used in string manipulation and shift oblique rotate instruction. DX, which is also known as data register, is used in order to host the port number while executing I/O operations or while performing I/O operations. In addition to that, it's also used in order to hold operand while performing multiplication and division instructions. Now let us move on to segment registers. Now there are four segment registers, namely code segment register, data segment register, stack segment register, and extra segment register. We have learned in the previous class that each of these segment registers are capable of holding the base address of the logical segments assigned to a given program. We have learned that in case of 8086, the overall memory is partitioned into logical groups called as segments of 64 kilobytes, which implies that for a given program in case of 8086, we can have 4 segments of 64 kilobyte, which further implies that out of 1 megabyte of total storage space in case of 8086 memory, a program can address up to only 256 kilobytes of memory or memory space. So there are 4 segment registers: code segment register, data segment register, stack segment register, and extra segment register that are capable of holding the base address of the logical segments. Now let us try to understand these segment registers in greater detail. So code segment register, it's a 16-bit register that stores the starting address of the code segment. In case of code segment register, we will be using offset as instruction pointer. So instruction pointer will be used in order to create displacement from the base address, that is CS, in order to refer to a specific byte in the code segment. Likewise, stack segment register, it's a 16-bit register containing the base address of the stack segment. By default, the processor assumes that all the data referred to by the stack segment pointer SP and BP is located in the stack segment. So here we'll be using BP and SP as the offset in order to create displacement from the stack segment register in order to access specific byte in this stack. Now likewise, a data segment register. It's a 16-bit register containing the address of the data segment or the segment where the program data is stored. By default, the processor assumes that all the data referred by general purpose registers AX, BX, CX, and DX and the index registers SI and DI is located in the data segment. So here we'll be using SI, DI, and BX as the offset in order to create displacement from the content of the data segment register in order to access specific byte in the data segment. Now likewise, extra segment register. It is a 16-bit register containing the base address of the extra segment. By default, the processor assumes that DI register refers to extra segment while performing string manipulation instructions. Now, these are the 4 segment registers and its description. So, code segment register is a 16-bit register that will store the base address of the code segment. Here we can use IP as the offset in order to create displacement to access specific byte in the code segment. Stack segment register is a 16-bit register that stores the base address of the program stack. Here we'll use SP and BP as the offset in order to create displacement to access specific byte in the stack segment. Data segment register is a 16-bit register that points to the program data. We have also learned that by default the processor assumes that all the data referred by the general purpose registers AX, BX, CX, and DX and index registers SI and DI are located in the data segment. So here we'll use the offset as SI, DI and DX. Now extra segment register is a 16-bit register containing the address of or holding the base address of the extra segment. By default, the processor assumes that DI register refers to extra segment while performing string related instructions. Now, it is also possible to change default segments used by the general and the index registers. This can be done by simply prefixing instructions with a CS, SS, DS or ES. So if we prefetch the general and the index in registers by the specific code segment registers, then we can change default segments. Now these are the four segment registers that we have in 8086. Now let us move on to the pointer register. So there are two pointer registers, SP and BP. SP stands for stack pointer and BP stands for base pointer. The stack pointer register points to the program stack. It is used in conjunction with stack segment register for accessing the stack segments or accessing the specific byte in the stack segment. Again, I'll repeat it. Stack pointer register is a register pointing to the program stack, and it's used in conjunction with stack segment register in order to access specific byte in the stack. Likewise, BP register stands for base pointer. This base pointer register is capable of pointing to the stack segment again. But unlike SP, BP can be used in order to point to other segments as well or access data in the other segments as well. So SP and BP are offset, which is used in conjunction with the stack segment register in order to access specific byte in the stack. Now index registers. We have two index registers, namely source index register and destination index register. Source index register, this is used in order to point to memory location in the data segment addressed by DS. Again, I'll repeat it. Source index register is used in order to point to memory location in the data segment addressed by DS. So it is used as offset with respect to DS in order to access specific byte in the data segment. So by incrementing the content of SI, one can easily access the consecutive bytes or data that are there in the consecutive memory location. So this implies that SI can be used in order to access the content of an array. Now likewise, DI stands for destination index register. Destination index register performs the same operation as that of or performs same function as that of source index register. The only distinction is that DI can be used in order to access memory of the extra segment while performing string related operations. So in case of string related operations, DI is used in order to access memory location of the extra segment or memory location addressed by the extra segment. So that is the only distinction between SI and DI. So both can be used in order to access the contents of an array. Now instruction pointer. Now instruction pointer is a 16-bit pointer that is capable of holding address of the next instruction that is to be executed. So instruction pointer points to the address of the next instruction to be executed. It is also understood that the content of the instruction pointer is auto-incremented when a particular instruction is being executed. So the content of instruction pointer is automatically incremented when the execution of a program proceeds further. So the content of the instruction pointer and the code segment register is used in order to create access to or in order to access a specific byte in the code segment. This implies that instruction pointer is used as an offset in conjunction with the code segment register in order to access specific byte in the code segment. Now let us try to understand flag register. 8086 has one flag register that is 16-bit in length. Out of 16 bits, 9 bits are active and 7 bits are left unused. Out of the active 9 bits, 6 bits are used in order to reflect status or condition, whereas 3 bits are used in order to reflect control. The 6 conditional or status flags are overflow flag, sign flag, zero flag, parity flag, auxiliary carry flag, and carry flag. Again, I'll repeat it. The 6 status or conditional flags are overflow flag, zero flag, sign flag, carry flag, auxiliary carry, and parity flag. Whereas the 3 control flags are direction flag, interrupt flag, and trap flag. So based on the results of the arithmetic operation, the 6 status flags are set. So if the result of an arithmetic operation is 0, 0 flag is set. If the MSB of the result is 1, then the sign flag is set. If there is a carry in case of addition and borrow in case of subtraction, then the carry flag is set. If there is a carry from third bit or borrow from the third bit in case of addition and subtraction operation, then auxiliary carry is set. If there are even number of ones in the lower order byte of the result, then parity flag is set. If there is an overflow in case of the arithmetic operation, that if there is an overflow from the 15-bit or the 7-bit, then the overflow flag is set. So these are the reasons why the status or the conditional flags may be set. Likewise, we have the control flag, we have trap flag, we have interrupt flag, and we have direction flag. So we have learned about these flag registers in detail in the previous class, so we will not be elaborating it. But for now, you need to remember that there is one flag register which is of 16-bit in length, out of which 9 bits are active and 7 bits are left unused. Out of 9 bits, 6 bits will represent status or condition, whereas 3 bits will represent control. Now, in today's class, what we have learned about is we have learned about 3 important features of 8086 microprocessor. We have learned about instruction queue and its utility. We have learned about the various operational modes of 8086 microprocessor, and then we discussed the programming model, where we have discussed the 14 CPU hardware registers of 8086 microprocessor. So in the upcoming classes, we will be discussing more features of 8086 microprocessor. Till then, thank you and goodbye.